everyone, welcome to our channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. आज हम कंप्यूटर ग्राफिक्स की क्लास करने वाले हैं जो कि क्लास नंबर 4 है। ऑलरेडी हम थर्ड क्लासेस कर चुके हैं। इन थर्ड क्लासेस में हमने यूनिट 1 पूरा कंप्लीट कर लिया है एंड नाउ वी आर गोइंग टू स्टार्ट विद यूनिट 2 विच इज़ योर ट्रांसफॉर्मेशन. And before starting with this, first of all, it's a huge request from my side to all the viewers. Please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. And they're talking about transformation here. The transformation, first of all, you have to know a short detailed about it with reference towards this chapter, what we'll discuss in the next coming classes and even though in this classes as well. So in the transformation, that is the transformation is used to position, reshape and animate object like that is your lights and the virtual camera, and to be the orthographically or prospectively project at the three-dimensional geometry on a plane as well, where a given set of points, polygon or a sampled parametric curve, that the transformations are done for the several purposes as well. Where we have to change the coordinate, that is your frames like world, a window, a viewport and a device, etc. Then we have to compose the object of simple parts with local scale, position, orientations of one part that is defined with the regard to the other part, for example for the articulate object as well. Then you use deformations to create a new shapes and then useful for the animation as well. So these were the four steps that how you can use for animation, and that is the transformations are in of three basic classes. The first is your rigid body, the second is your conformal, and the third is your affine. In this, the rigid body, that the distance and the single angles that are preserved, like for example that the translations and rotations has been taking place. The conformal here, that the angle is preserved here, so here the translation rotations are uniform scaling, and as well as in an affine, that the parallelism or the lines that remain the lines is preserved, and with regard of it, example is the translation, relaxation, rotation, scaling, shear and reflections that comes under affine here. And other than that, we'll discuss about the basic transformation, which is your translation, scaling and rotation. And in the matrix representation, that the row major and the column major representation that we'll discuss here. About the homogeneous coordinates, where we'll discuss about it, that in order to represent the translation as a matrix multiplication operation, we use a 3x3 matrix and a pad our point to become 3 into 1 matrix, and this coordinate system that is using the three values to represent a 2D point, that is called a homogeneous coordinate, and where the homogeneous coordinate consists of pending one and or an x and y coordinate as well. There are various reasons for the working with the homogeneous coordinates are: the first is your simpler formula, second is your fewer spatial case, third is unification and extensions of the concept in 2D and 3D space, and the fourth is your duality as well. In the same reference, we'll discuss about the composite transformation, where we'll have to go ahead with how to combine the several transformation operations, like example is to rotate and then translate, or the reverse, that is translate and then rotate, or the two rotations, that is rotate this amount then that of amount, and then of course the even more complex, which is the scale and then rotate then translate. So these comes under in it one by one. After that, the matrix multiplication, that is associative non-commutative transform matrix that must be pre-multiplied, and that the first transformation that you want to perform will be the far right just before the point as well. So now we'll discuss about it each and everything with reference towards the reflections, and of course the shearing we'll discuss about it. So let's go ahead with the detailed here, and that is why image translation is necessary and important in computer graphics, and explain any one of the image translation method as well. So first of all, we'll discuss about image transformation. In image transformation that is necessary and important in computer graphics, and explain the one image transformation method. That's what we have to discuss here. So here, if we want to make any changes in the image, then there is a need of transformation, and the transformation that include is that we have here we have 5. So the first we have is your translation. The second is your rotation. And the third we have reflection. The fourth we have scaling. And the fifth and the last is just sharing. These were the 5 image transformation that take place here when you have to change an image. And the other question is that what are the basic transformation? Describe each with their matrix representation. So first we'll have to represent in the form of the matrix representation as well, and the basic transformation that we will discuss here. The basic transformation here, that the following are the various basic transformation. The first, as I told you, about the translation, so that we'll discuss here. In the translation, that a translation is applied to an object by representing that repositioning it along a straight line path from one coordinate location to another. We translate a two-dimensional point by adding a translation distance, which is Tn, Ti, Tx and Ty, and that to the original coordinate position, which is x comma y, to move the point to a new position as well, which is your x dash and y dash. So in the same references we will be having here is in the form that is the equation it form x dash equals to x plus t, and y dash equals to y plus t as well. So the translation distance, the pair that is of tx and ty, is called a translation vector, and above equation that can be represented in the form of the matrix, and that will be in the structured form if I'm representing here. This is y, this is a point p till this is a p dash point. So here this is a point p. So with the preference towards a p here, that is equals to x1 x2, and p dash that is equals to x1 dash x2 dash, and the t here that is your tx ty, and of course the p dash is equals to p plus t. So hence the translation in the rigid body transformation that moves about object without deformations, and similar method that are used to translate the curve object, and to change the position of a circle or the ellipse we translate the center coordinate as well. Now we'll discuss about the second one, which is your rotation. In the term of the rotation, here a two-dimensional rotation is applied to an object by rotating it along a circular path in the xy plane, and to generate a rotation we specify a rotation angle theta and the position xr and the yr of rotation point about which the point is to be rotated, and the positive values for the rotation angle define the counterclockwise rotation about the pivot point, and a negative value that rotate object in a clockwise direction as well, where the transformation that can be described as the rotations about the rotation axis that is perpendicular to the xy plane and passes through the pivot point as well. So we'll represent it in the form of a figure here. This is your x dash y dash, and this is comma x comma y, where this is r, this is r, this is theta, and this is phi. So in the above figure, that using the standard trigonometric identities, that we can express the transformed coordinate in the terms of the angle that is angle theta, and of course the null as well, and phi, you can say that as follows. So we'll go ahead with the equation here, and that's what we have to follow as well. So here that the equation we have, x dash equals to r cos theta, r cos theta equals to r cos theta minus r sine sine theta. And for the y dash, which is equals to r sine phi plus theta equals to r cos sine theta plus r sine phi cos theta. So this has been represented here, that the original coordinates of the point in a polar coordinate that are to be followed as well, and that is to come across it, and which is your the same one as to be like x equals to r cos phi and y equals to r sine phi. So we are putting in the above equation here. So what we will get in the form of, and that what we have to discuss here, and there is in the representation of the file, solving it out, we'll go ahead in a detail, which is your x dash x cos theta minus y sine theta, and y dash equals to x sine theta plus y cos theta here. And in the same references, we can write the relation equation in the matrix from the figure that we have is your p dash rp. So when the rotation of the matrix takes place, then we will be getting r equals to cos theta minus sine theta cos theta. This will be the r. And if talking about p, so p dash equals to x dash y dash, and talking about p, so that is x y. So this is about the rotation here. Now I'll talk about the third one which we have, and that is your scaling. In the scaling here, where a scaling transformation alters the size of an object, and this operation that can carried out for polygon by multiplying the coordinate value, which is x comma y of each vertex by scaling factor, which is of sx and ssy, that to produce the transformed coordinates x dash and y dash as well, where in the same case x dash equals to x and sx as well, y dash is equals to y dot xs as well. That the scaling factor of the s scales that object in the x direction, while sy scales in the y direction. The transformation equation that can be written to be in the form of the matrix form, so that has been represented in the form of x dash y dash equals to sx 0 0 sy multiply by x and y. So this is where S is a 2 cross 2 scaling matrix, and where the values less than 1 that reduce the size of an object, and values that is greater than 1 that produces an enlargement. So specifying is a value of 1 for the both Sx and Sy that leaves the size of an object unchanged, and when an Sx and Sy that are assigned to the same value and a uniform scaling is produced, then the maintains relative object proportion as well, and unequal values for Sx and Sy that results in the differential scaling that is often used in the design application, and where pictures are constructed from a few basic shapes that can be adjusted by the scaling and positioning the transformation as well. So before scaling and after scaling, that will represented here. So before scaling it would be like in the form of this, but and after scaling it would be like in the form of this. So this is the before scaling and this is your after scaling here. Now we'll discuss the another question which has been asked here, and that is the what do you understand by homogeneous coordinates, and that is has been asked for 5 marks. So let's go ahead to discuss about it, which is homogeneous coordinates. In the homogeneous coordinate, the term homogeneous coordinate is used in mathematics to refer to the effect of the representation on a Cartesian equation, and when a Cartesian point x comma y is converted to a homogeneous representation, which is x h and y h and h, that the equation that containing the y, and where the f of x comma y is equals to 0. So where that becomes the homogeneous equation in the 3 parameter, which is xx and yh and h here, that is in the form of the equation, the coordinate we have. And that is for this, that this just mean that if each of the 3 parameters is replaced by any value v times that parameter, and that the value v that can be factored out of the equation and expressing the positions in the homogeneous coordinate, that allow us to represent all the geometric transformation equation as matrix multiplication. The coordinates are represented with the 3-element column vector, and transformation operation are written as a 3 by 3 matrix for translation we have. So for that we'll go ahead here as well, that is in the representation x dash y dash 1 1 0 dx 0 1 dy and 0 0 1, that is our x, y and 1. So here which we can write in the abbreviated form of, like in the form we can represent it as p dash equals to t of x, t of y, and that p as well. So here we have to note that the inverse translation matrix that is obtained by replacing the translation parameter, which is tx and ty, with the negatives, that is 0 minus tx and minus dy as well. Similarly, the rotation transformation, that equation about the coordinate origin, that are the new written to be as in the form of which we will be representing here in the form of the homogeneous coordinates here. So that is x dash y dash 1 equals to cos theta minus sin theta 0 sin theta cos theta 0 0 0 1. This is x y 1. So this has been represented in the form of like p dash equals to r theta t. So here that we get the inverse of the rotation matrix when theta is replaced with minus theta, and finally a scaling transformation related to a coordinate origin is now expressed as matrix multiplication, and that is in the form of I will represent it here, and that is would be represented in the form of like x dash y dash 1 equals to sx 0 0 0 sy 0 and 0 0 1, that is multiplied by x y and 1, and which will be giving is in the form of p dash equals to s s x s y dot p as well. So that replacing these parameters with a multiplicative inverse, and which is your 1 by third 1 by s of x and 1 by s of y, that yields the inverse scaling matrix as well. Now we'll discuss about another one which is in the detail as well, that is in the form of what we have to discuss here, and that is prove that two successive translations are additive, and or otherwise they had asked you about discuss the composite transformation with relevant examples. So first we'll discuss about the composite transformation, and then we'll discuss about the translation as well. So here we'll go ahead. composite transformation, in the case of the composite transformation, that we can set up a matrix for any sequence of transformation as a composite transformation matrix by calculating the matrix product here, and that is of the individual transformation. And talking about the translation, that if the two successive translation vector, which is of tx1 and ty1 and tx2 and ty2, so that are applied to a coordinate of the position p, then the final transformed location p is to be as calculated as in the form of, which is p dash equals to t tx2 ty2 tx1 ty1 multiplied by p. So this is what it would be represented in the form of. Now we'll further go on ahead. So here we'll discuss about it, which is that tx2 and ty2 and tx1 and y1, that p as well, where p and p dash that are represented as a homogeneous coordinate column vector. We can verify the result by calculating the matrix product for the two associative grouping, that is the composite transformation matrix for the sequence of translation is, and that has to be represented in the form of, and where that has been representing here in the form as represented as well, which is 10 tx2 0 1 ty2 and 0 0 1, then that is multiplied by 10 tx1, and that is your 0 1 ty2 and 0 0 1, that will give you 10 tx2 plus tx1, then that is 0 1 ty2 plus ty1 and 0 0 1 as well, so that it will represented you, and that it will give you as in the form of. And while solving it further, we will be finding out is the equation will be finding out in the form of t t2 tx2 ty2 tx1 ty1 tx1 plus tx2 ty1 plus ty2, so which demonstrate that the two successive translations are additive here. So now we'll go ahead to discuss about the another question, which is your show that the compositions of the two rotation is additive by concatenating the matrix representations of r theta 1 and r theta 2 as well, to obtain the r theta 1 multiply r theta 2, which will give you r theta 1 plus theta 2 here. So let's go ahead to discuss about it. So that we have to obtain is it is r theta 1, and that is we have an absolute r theta 2, which will give r theta 1 plus r theta 2 as well. So here that first we will rotate an object by an angle theta 1 and through the origin in the anti-clockwise direction, then the required matrix will be finding out in the form of, which is your cos theta 1 minus sin theta 1 0 sin theta 1 cos theta 1 0, and that is your 0 0 1. Similarly, again we will rotate the same object in an anti-clockwise direction by an angle of theta 2, then by the required matrix. So what will be finding it out, that is in the same case the same thing we will find it out, but in the same case we will be having a theta 1 here, and in this that will be having a theta 2 cos theta 2 sin theta 2 and 0 minus sin theta 2 cos theta 2, that is 0 0 0 1. For now, for r theta 1 and r theta 2, that what we have to multiply here, So we'll go ahead with this. That is your r theta 1 multiply r theta 2. So let's go ahead to multiply here, which is your cos theta 1 minus sin theta 1 0 sin theta 1 cos theta 1 0, and that is 0 0 1. The other we have is your cos theta 2 minus sin theta 2 0 sin theta 2 cos theta 2 0 0 0 1. So here in the same case we will be solving it out in a further way, which is cos theta 1 cos theta 2 minus sin theta 1 sin theta 2, and here we'll multiply with row and columns, then we'll find it out. Minus cos theta 2 1 sin theta 2 sin theta 1 cos theta 2, and then 0. So here the another row will find it out. Sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. Here we'll get it sin theta 1 sin theta 2 plus cos theta 1 for cos theta 2, and then we have 0 as well. The other case is your 0 0 and 1. So that will get it out here. And in the same cases we'll go ahead with the further one, that to solve it out the further way with a formula. So that is your the cos theta 1 plus theta 2. This is your minus sin theta 1 plus theta 2, and this is 0 sin theta 1 cos theta 2 plus, and here in this will be finding it out is your cos theta 1 plus theta 2. That is your 0. Now we'll be getting is your 0 0 1, and here in the same case, that is r theta 1 r theta 2 equals to r theta 1 plus theta 2. That is hence proof that it will required of what they had asked you is what we had proved here. Now we go ahead further one, and that is another question that what we have to solve it out, where we have to solve it out like show that uniform scaling and rotation makes a commutative pair, but in general scaling and rotations are not commutative. That has been asked for 6 marks. So that what we have to solve it out here. So the question is, I'll just write it down. Show that uniform scaling and rotation make commutative pair, but in general scaling and rotation are not commutative. So for a two-dimensional transformation, the general scaling we have is and for the rotation we have sine theta, cos theta, 0, 0, 0, 1. So in the same reference, according to the commutative property, where that is your scaling, rotation and rotation scaling, that will be equal there. So we'll go ahead with the talking about SR equals to RS. So we're taking the left hand side, which is SR. So talking about this, that we have SR equals to S of x 0, 0, and that is 0 sy 0, 0, 0, 1, and here cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. It will give you sx cos theta minus sx sine theta 0, where sy sine theta, sy cos theta 0, this is 0, 0, 1. Now taking an RHS side, that is your RS. So here in this, that is your cos theta minus sine theta 0, here sine theta cos theta 0, and that is 0, 0, 1. Here, which is x 0, 0, 0, sy 0, and 0, 0, 1. For that, we'll get it out as your sx cos theta minus sy sine theta 0, sx sine theta, sy cos theta 0, 0, 0, 1. So here, using the general scaling, and a commutative property is not satisfied here, and when sx and sy that are assigned the same value and a uniform scaling is produced, so let sx equals to sy, which is equals to as well 1. So in the same cases, we can say that the scaling and rotation is equals to rotation and scaling is equals to 1. So we can prove that is a cos theta sine theta 0, sine theta cos theta 0, 0, 0, 1, which is equals to cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. That is, hence the commutative property is satisfied for the uniform scaling. So this has been proved here. Now we'll go ahead with another question. That is, the another question has been asked. Prove that the inverse of the rotation by angle pi, that the degree, and as the rotations in opposite direction. That what we have to prove here. So let's go ahead further to solve that particular question here. So the other question we have here, prove that the inverse of rotation by angle by degree is the rotation in opposite direction. So in this, we'll have to solve it out, which is your comes under in it, and that is that what we have to discuss about it. So in the same cases, that the rotation that is anticlockwise direction matrix by an angle phi that we have is your r equals to cos phi minus sin phi 0, sin phi cos phi 0, 0, 0, 1. For this, we'll be solving it out, and the inverse of it, the inverse of rotation this, then we have your R inverse. We'll rotate it out. This is your cos minus phi minus sine minus phi, which is 0. Then we have your sine minus phi cos minus phi 0, and that is 0, 0, 0, 0, 1, so that it will be find it out. So now since that cos minus theta is equals to cos theta, and sine minus theta is your minus sine theta, so we'll solve it out with this, and that is we'll find it out R and phi, which is equals to cos phi sine phi 0 minus sine phi cos phi 0, 0, 0, 1. So therefore the inverse of the rotation by an angle phi degree is the rotation matrix in the clockwise direction. Now we'll discuss about more in the detail, which is another question. Rotate the triangle, which is A, that is your 2, 2, B 4, 2, C 4, 4 by 90 degree about the origin, which is in anti-clockwise direction here. So let's go ahead to solve it out. Rotate the triangle, which is A 2, 2, B 4, 2, C 4, 4 by 90 degree about the origin, that is your anti-clockwise direction. So here we'll solve it out this, and that is the relation matrix about the theta, that is equals to 90 degree. So for that we have R equals to cos theta minus sine theta 0 sine theta cos theta 0, 0, 0, 1. With the triangle matrix, if I'm talking about the triangle matrix we have, which we will talk about it, triangle matrix, and that is equals to 2, 4, 4, then 2, 2, 4, and 1, 1, 1. So P dash is equals to R multiply P. So here, so we will solve it out here as well, which is cos theta minus sine theta 0 sine theta cos theta 0, 0, 0, 1. That is your abstract. That is 3 cross 3, 2, 4, 4, 2, 2, 4, and 1, 1, 1. So that will go ahead, which is 0 minus 1, 0, 1, 0, 0, and 0, 0, 1, 2, 4, 4, 2, 2, 4, and 1, 1, 1. That will give minus 2, minus 2, minus 4, 2, 4, 4, and 1, 1, 1. So here in this, that is A dash is equals to minus 2, 2, B dash is equals to minus 2, 4, and C dash is equals to minus 4, 4. So now we'll go ahead to discuss about in a detail, that is prove that 2D rotation and scaling are commutative if theta equals to n phi. So that what we have to discuss here. So here we'll discuss the another question, which is prove that 2D rotation and scaling are commutative if theta equals to n phi. So here the required matrix for the rotations and scaling we have, which is your r strict s, that is equals to cos theta minus sin theta 0, sin theta cos theta equals 0 0 0 1, that is sx 0 0 0 sy 0 0 0 1, which will give you cos n phi minus sin n phi phi, and that is your 0, sin n pi cos n pi and 0 0 0 1. And here the matrix we have, which is your S matrix, Sx 0 0 0 Sy 0 and 0 0 1. So further multiplying with this, the cos n phi we have here, that is cos n phi is 1, then 0 and then 0. This is 0 1 0 0 0 1. And the same matrix for this, we have Sx 0 0 0 Sy 0 0 0 1. And the same reference towards it, that what will multiply in it, and we'll be finding out r abstract s as well. So that is in the form of r abstract s, which is equals to Sx 0 0 0 Sy 0 and then 0 0 1. So here that is similarly we can say that for the r multiply sr, which is equals to Sx 0 0 0 Sy 0 0 0 1, that is multiplied by cos n pi minus sin n pi 0 sin n pi cos n pi 0 and then 0 0 1. Here we'll talk about it SR, which is equals to Sx 0 0 0 Sy 0 and then 0 0 1. So that comes under in it is that for that sake, for equation 1 and 2, that this is for the r into s, the equation 1, and this is an equation 2, that as it is clear that the 2D rotations and scaling are commutative for the theta equals to n pi, and so that there is r cross s and s cross s, that is equals. So that hence proved here what they had asked you about it. Let's go ahead with another question, and that what we have to solve it out, and that is the write the transformation matrix for a given scaling transformation. The first part is that the entire image is reduced to the half size of the original image. अगर original image का half size कर दिया जाए, then what you will be finding out that's in the form of a matrix. So here, since the entire image is reduced to half size, this means that Sx, that is Sx equals to Sy, which is equals to half. So for the scaling matrix we have here is scaling matrix, which is equals to Sx 0 0 0 Sy 0 and 0 0 1, which is equals to half 0 0 0 half 0 0 0 1. Now the second question has been arrived that the entire image is reduced to 1/3 of the original image. So for that, Sx and Sy is equals to 1/3. So we'll do that the same thing. The scaling here, scaling matrix equals to 1/3 0 0 0 1 by third, 0 0 0 1. Now for the third one, the third case is that the entire image is 3 times larger than the original image. So that means S6 and Sy is equals to 3. So the scaling matrix will be finding out is for the third one, which is the scaling matrix equals to 3 0 0 0 3 0 and 0 0 1. The another question has been arrived here, and that is in the form of that the x length is reduced to by third of the original value and the y length is unchanged. So for that, what we have to find it out, and that we have here is, and that is Sx is equals to 2 by third and Sy is equals to 1, and for that we have a scaling matrix equals to 2 by third, 0 0 0 1 0 and 0 0 1. The another question has been arrived here, that is the x length is unchanged and the y length is the 2 times of its original change. So that is Sx is equals to 1 only and the Sy is 2. So for that, a scaling matrix here, this is the fifth one, equals to 1 0 0 0 2 0 and then of course 0 0 1. So this has been proved here. Now we'll go ahead with another question, and that what we have to discuss here, which is the another question, and that the question is to be as follows. We have to discuss here. So the question is that show that the compositions of two scaling in a is multiplicative by concatenating the matrix represented by S, which is your, that is S Sx1 Ss1. We'll go ahead with the discussion, and that what we have the another one, which is your Sx2 Sy2, that to obtain the solution that we have here as Sx2 Sy2 Sx1 Sy1, and that is equals to Sx1 plus Sx2, and that plus Sy1 plus Sy2. So here we'll discuss about the scaling, which is the scaling is your concatenating the transformation matrix for the two successive scaling operation that is produced for the following composite scaling matrix as well. So that what we have here is to be as follows. The matrix we find it out is in the form of, which is there is Sx2 0 0 0 Sy2 0. That is here the matrix, we'll find it out, and which is in the form of 0 0 1. So here we have Sx1 0 0 0 Sy1 0 and then 0 0 1 as well. That will give Sx1 S, that is your x2 0 0 0 Sy1 Sy2 0 and then 0 0 1 as well. In the same cases, we'll go ahead with the finding out the equation as well, which we will be provided as in the form of that is your Sx2 Sy2, which is your Sx1 Sy1 S, that is your x1 y x, that is your Sx2 Sy1 Sy2. The resulting matrix in this case that indicate the successive scaling operation that are multiplicative as well. Let's go ahead to discuss about the another thing that what we have to discuss here is to rotate that the triangle A equals to 0 comma 0 and B equals to 2 comma 2 and C equals to 10 comma 2, then about the point P, which is your minus 1 comma minus 1 by an angle of 45 degree, where we have to find it out for this. So let's go ahead here and we'll go ahead with the first, we'll go ahead with the question here. Here we'll go ahead with this, that is to rotate the triangle A equals to 0 comma 0, B equals to 2 comma 2, C equals to 10 comma 2. About the point we have, that is a P equals to minus 1 comma minus 1 at a 45 degree. So this is what it consists of, and that is to required matrix we have here is to be as follows, which is P equals to T, that is minus 1 comma minus 1, abstract R, abstract T 1 comma 1, and which is abstract P as well. So here we have a matrix we will multiply and then we'll find it out solution at the angle of 45 degrees. So let's go ahead here. So we will have a matrix here, that is your 1 0 minus 1 0 1 minus 1 0 0 1 multiplied by cos 45 degree minus sine 45 degree 0 sine 45 degree cos 45 degree 0 0 0 1. That is also multiplied by 1 0 1 0 1 1 and 0 0 1. So here in the same case the another matrix we have, that is your 0 to 10 0 to 2, and that is another one is 0 1 1 1. So in the same case we'll find out matrix here, that is in the form of 1 minus 1 minus 1 root 3 by 2 minus 1, that is your root 2 minus 1 2 root 2 minus 1 and root 9 upon 2 minus 1. The other is your 1 1 1. So here with this A n r pi, that is your equals to minus 1 comma under root 2 minus 1, B r, that is equals to minus 1 2 root 2 minus 1, and near C is equals to root 3 upon 2 minus 1 9 root 2 upon minus 1. So that is comes under in it. Now we'll discuss the other question which has been asked here, to derive the reflection matrix for the reflection about the x-axis, and that is your to explain establish the reflection transformation matrix about the line which is equals to y equals to mx plus b, and that has been asked for 6 marks. So in this, that the reflection of an object is a reflection of a transformation that produces the mirror image of an object, and if ABCD is an original position, then in a rectangle for the x-axis and y-axis, the reflection about the x-axis, if the reflection is about the x-axis, which is x dash equals to x and y dash is equals to y, and in the same case y dash is equals to minus y. So the original position and the reflection position is all in the opposite direction, and for that we have a matrix here, that is P dash equals to R reflection multiplied by P. So that is we have an equation here, that is x dash y dash 1, and that is equals to 1 0 0 0 minus 1 0 and 0 0 1, that is multiplied by x y 1. The reflection about the line, that is your y equals to x. The reflected positions and the origin positions are one another, and for that, for p of dash, that reflection matrix we have is the same, that is your in the reflection action for that, another triangle we have here, and that is in the form of x dash y dash 1 equals to 0 1 0 1 0 0 and 0 0 1 multiply by x, y and 1. So here the similarly the reflection matrix about a line here, and for that we can say here y equals to minus x, that is your p dash equals to r of reflection y, and that is multiplied by p. So for the implementation of this, we will be having here, that is in the term of x dash y dash 1 0 minus 1 0 minus 1 0 0 0 0 1, and that has been multiplied by x, y and 1. And the reflection of an object about any line, like let a line L, that is your y equals to mx plus b, have a y-intercept which is 0 comma b and an angle of theta with respect to axis, and we reduce the descriptions to known transformation. And the first we have to translate the interaction between points p to the origin, then rotate by minus theta degree, so that the line L aligns with the x-axis, and then mirror reflect about the x-axis and rotate back to the theta, and then translate b back to the theta, that is 0 comma b as well. That has been the reflection of a point p about a line as well. So in the same cases, we'll go ahead to discuss about the another one, which is your that what are homogeneous coordinates, and if the line whose end points are x1 and y1 and x2 and y2 then exist in a 2D space, then write the concatenation of matrix that will rotate the mirror image of a line about midpoint of a line by an angle of 60 degree counterclockwise, and each of the transformation has to be in the homogeneous coordinate system. So homogeneous coordinate we had discussed about it, and that what we'll discuss about in a detail, that is the question is reference towards the two endpoint. So let's go ahead with this, and that as we know that the first we have to translate the line of the origin. Once it is origin, then we have to rotate it in there, and then again translate back into the original position. So let for that will be let the given line that will understood about it. So here let the given line is x1 y1 is less than x2 y2. So that will be represented in the form of, and that what we have, even though we have to solve it out as well. So here in the step 1 the rotation has been taken place, and that for that sake that the rotation has been taken, and this is step 2, that the shift to the origin and translation, then take mirror reflection through an angle of 60 degree, and then of course that new equation will be found out, and the combined equation will be formed up in the form of translation, rotation and again translation. So the equation we have for the following is, which is x1 y1 1 give 1 0 h 0 1 k, and that is 0 0 1. This cos 60 degree minus sine 60 degree 0, and that is your another one is your sine 60 degree cos 60 degree 0 0 0 1. The other matrix with reference towards it that we have is 1 0 h minus h 0 1 minus k and 0 0 1. Now for that, representing in the form of x2, that is x2 dash y2 dash and 1 1 0 h dash 0 1 k dash, and then we have 0 0 1 cos 60 degree minus sine 60 degree 0 sine 60 cos 60 0 0 0 1, 1 0 minus h dash, 0 1 minus k dash, and 0 0 1. And the same reference towards it, which is your h equals to x1 and k equals to y1, and where h dash is equals to x2 and k dash is equals to y2 here. Let's go ahead with other question, that is to show that the reflection about the line y equals to minus x is equivalent to the reflection relative to f y-axis and followed by an anti-clockwise rotation by 90 degree of that what we have to solve it out. So let's go ahead to solve in a detail as well, which is show that the reflection about the line, that is your y equals to minus x, that is equivalent to the reflection relative to the y-axis, that is followed by the anti-clockwise rotation at 90 degree. So reflection matrix about line matrix, that is y equals to minus x, as I told you about it. So here that we have is matrix is your 0 1 minus 1 0 minus 1 0 and 0. This is 0 0 1. So here the reflection matrix about the y-axis we have, which will be is your minus 1 0 0 0 1 0 and 0 0 1. So for that rotation matrix we'll talk about it. Cos 90 minus sin 90 0, that is your sin 90 cos 90 0 0 0 1, which is equals to as well 0 minus 1 0 1 0 0 and 0 0 1. In the same case the reflection, then the rotation composite matrix we have, and that is in the form of 0 minus 1 0 1 0 0 and 0 0 1 minus 1 0 0, then you have 0 1 0 and of course 0 0 1, which is give 0 minus 1 0 minus 1 0 0 and 0 0 1. So which is equals to the transformation matrix for the reflection about the line, which is y equals to minus x. Now we'll go ahead to discuss about the another question, and that what we have to discuss here. The other question is to be as follows, that show that the reflection along a line which is y equals to यहाँ पे minus x के लिए solve किया था. Here we have to solve for the y equals to x, that is equivalent to the reflecting along the x-axis, where that we have to discuss about y-axis, that is follows as an anti-clockwise direction in the rotation, that is your 90 degree. So let's go ahead to solve it out, where y equals to x. So the matrix we have 0 1 0 1 0 0 and 0 0 1. So for that now the reflection matrix about the x-axis we have is that is be representing as 0 1 0 0 and 0 minus 1 0 and 0 0 1. And for the rotation matrix we have, which is rotation at 90 degree, which is a cos 90 minus sin 90 0 sin 90 cos 90 0 0 0 1, which is equals to 0 minus 1 0 1 0 0 and 0 0 1. So here the reflection, then the rotation composite matrix we will be finding out, and that is here is to be follows. That is your 0 minus 1 0 1 0 0 and 0 0 1 1 0 0 0 minus 1 0 and of course 0 0 1, that is equals to 0 1 0 1 0 0 and then 0 0 1, which is equivalent to the reflection matrix about the y equals to x as well. Now I'll go ahead to discuss about the another question, and that is in the form of show that a 2D reflection through an x-axis followed by a 2D reflection through a line, that is a y equals to minus x, that is equivalent to the rotation of theta 270 degree about the origin. So the equation we have for a line that is y equals to minus x, and that an x-axis of the reflection, the transformation matrix of the reflection about the x-axis of the reflection, that is about the y equals to minus x, that should be. And in the same form we have 0 minus 1 0 minus 1 0 0 and 0 0 1 equals to 1 0 0 0 minus 1 0 and then 0 0 1, which is here, that is an abstract, equals to 0 1 0 minus 1 0 0 and then of course 0 0 1. For that, the required rotation matrix we have is at the rate of theta equals to 270 degree. So where we have will be finding out as your r 270 degree, that is equals to cos 270 minus sine 270 and 0, sine 270 cos 270 0 0 0 1, that is equals to 0 1 0 minus 1 0 0 and 0 0 1. So which is equals to the matrix that is here 1 here. Now we'll go ahead with the discussion about the another one, and that is very important as well, and that can let you about the another question as well. So for that we will be doing further one of it, and then we'll discuss by the another thing in the next coming classes as well. So here we'll discuss some of the theory, because we had done many of the things in the numerical here. So that we'll go ahead to discuss about it, and then we'll discuss some of the things in the terms of it, and that is comes under in it. And in the same cases that what you have to understand about it in this, that is we'll talk about it, explain the transformation between the coordinate system and an appliance transformation as well. In the same cases, for that that the coordinate system and appliance transformation that are discussed to be like the coordinate system is in the mathematics the homogeneous coordinate system that allow to be easily represented by a matrix, and also they can make the calculation possible in the projective space just as Cartesian coordinate, and doing the Euclidean space as well, and that the homogeneous coordinate of that point of the projective space of dimension, and that are usually written as in the form of x, y, z until w, that a row of the vectors of length n plus 1, and other than that, that is 0 0 0 till the 0 here, that the two sets of the coordinate that are proportional denote that the same point of the projective space as well. In the same cases that for any non-zero scalar c from the field underlying field k, that is cx, cy, cz till cw, that denotes that the same point, and therefore the system of the coordinate that can be explained as to be follows here. If the projection space is to be constructed from the vector space v of the dimension n plus 1, that introduces the coordinate in a v, and by choosing a basis of the use of these p of v, that the equivalence classes of the proportional, that is non-zero vector and v as well. We are taking the examples of the projective space of the dimensions 3, that there will be the homogeneous coordinate x, y, z and w, and that is the plane of the infinity is usually identified with the set of the point with w equals to 0, and that is away from this plane. We can use that an ordinary Cartesian system, therefore that the affine space that is complementary to the plane at infinity is coordinated in a familiar way with the basis of corresponding here. And in the same cases the affine transformation has been also taken about, and that what we will talk in a detail in the next coming class. So first of all, it's a huge request from my side to all the viewers, please go through the subscribe button and please like, share and subscribe to our channel, so that many and maximum people can get the information at once, and even you can also enjoy the video as well. And in the same cases, you will be finding each and every video here in reference towards the computer graphics, and of course the economics, database management system, and that is data warehouse and the data mining, as well as the principle of programming languages. You will be finding out the reasoning classes as well that we are doing, even though we are doing a quantitative aptitude as well. In talking about in the terms of the computer graphics here, so in this we had done unit 1 and we had started with unit 2. In the unit 1, this is your graphic devices which we had completed. That is your introductions and line generations, types of the computer graphics, graphic display, random scans display, raster scan display, frame buffer and a video controller, point and lines, line drawing algorithm, circle generating algorithm, midpoint circle generating algorithm, and a parallel versions of these algorithm as well. In unit 2, which is your transformation, we had started discussing. That is your transformation we had completed, the basic transformation, the matrix representation we had completed, homogeneous coordinate we had completed, composite transformation we had completed, reflection and the shading that we have to start with the next some task. Then we'll start with discussing about as well as about windowing and clipping, viewing pipeline, viewing transformation, 2D clipping algorithm, line clipping algorithm such as coincidence Sutherland line clipping algorithm, Liang-Barsky algorithm, line clipping against non-rectangular clip window, polygon clipping, Sutherland Hodgman poly clipping, and Wheeler and the Arthurson polygon clipping, curve clipping, and of course the text clipping as well. That's what we have to discuss. The unit 3rd, we have to start with the 3-dimensional, which is your 3-dimensional, 3D geometric primitives, 3D object representative, 3D transformation, 3D view projection, and 3D clipping as well. In unit 4, we have to start discussing about the curves, and that is your the curves and the surfaces. So the curves and the surfaces and the quadratic surfaces, the spheres, ellipsoid, a blobby object, introductory concept of spline and B-spline and the Bezier curves and surfaces, hidden lines and surfaces, backface detection algorithm, depth buffer method, a buffer method, and as well as scan line method, basic illumination models, ambient light, diffuse reflection, spectacular reflection, and a Phong model, combined approach, one model, intensity attenuations, color concentration, transparency, and shadow as well. And of course we'll have to discuss about very short answer type question here. So first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once. And even though you can also enjoy the video as well, you will be provided each and every video here. Thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion in a comment box. Thank you.